developing models. So we heard before the lunch a talk on observation of extrasolar disks. Now we hear about meteorites and what the meteorites have to say about planetesimal accretion. They give a lot of constraints on chemistry, temperature, chronology, so on, as basic constituents, building blocks, so on and so forth. So Matthieu Gounelle from Muséum, National History in Paris will tell us everything about that.
Thank you, Alessandro. Thank you for coming, for having resisted English college food and not being all asleep. And I'm very happy to try to present you the constraints on meteorites. There are many of them, far too many. So I made a selection. Obviously, this is my selection. I've tried not to be too much biased, and I hope it will be the case. Okay, meteorites. Meteorites are complex extraterrestrial rocks, okay? So never forget that these are rocks which you can handle in your hands and which you study in the lab with the same tools as geologists study terrestrial rocks. This is very important. I will not go through the classification because I don't want to bore you to start with, but very important and very complicated first to understand what kind of meteorites you are looking at. So obviously meteorites are important because they are the building blocks of the planets of our solar system. Okay, so you go from meteorites, so this might be 10 centimeter, 20 centimeter across, to planetesimals or asteroids, call them whatever you want, to planets. And basically, this is one of our most important constraints on planetary formation, together with the new beautiful observations we have of extrasolar planets, and also with a study of star-forming regions, like this one, which is maybe a 3 million year old star-forming region with a very massive star, which has created an H2 bubble, and disk, about which we heard a very nice talk this morning. So I'm not gonna concentrate at all on that because you already had an excellent talk, although this is something I'm quite interested in usually. Okay, so you have to distinguish basically two types of meteorites, okay? If you want to forget the whole complicated classification I showed at the beginning, and I encourage you to do so, you should remember that chondrites come from small bodies from the solar system, asteroids and comets, which might be from a few hundred of meters across to a few kilometers across. And differentiated meteorites or evolved meteorites come from larger bodies, such as Vesta, a large asteroid, maybe 800 kilometers across, or the planet Mars. The basic difference between the meteorites coming from these bodies and the meteorites coming from that bodies is that these ones have not evolved since the formation, and this one the planetary bodies have changed a lot since the formation. So how do they look like? So this is a typical differentiated meteorite, probably coming from Vesta, and it looks very much as a terrestrial rock. Okay, a non-expert geologist would just think this could be a terrestrial rock with angular inclusions and minerals you commonly find in terrestrial rocks. And this is a primitive meteorite, Murchison, a chondrite, and this is very different from any terrestrial rock. It's very rich in organic matter, and it is characterized by a large number of these round inclusions, which are called chondrules, and which give their names to the chondrites. Chondrules come from the Greek chondros, which meant little sand pebble. So chondrites, what are they? And why are they so important? Because they're basically cosmic sediments. It's like a sediment, but which comes from space, and it's made of three main components: CAIs, calcium aluminum-rich inclusions, chondrules, and matrix. So this is just a meteorite which has been cut. It's Léoville, the same type as Allende, of which you have probably heard. And the white stuff, are the CAIs, which you can see in this peculiar meteorite are quite abundant. And chondrules are all these little spheres, which in that case are elongated due to some secondary process on the parent asteroid. And the matrix is just a small segment which brings everything together.
Sorry, Matthew, when you say cement, does that mean is water helpful in making it bind?
In some of the matrix you have some water, but in some you don't. So cement was more a metaphor than a reference to construction techniques, which I don't know. So why do we study chondrites? So basically because we believe that chondrites components, such as CAIs, chondrules, and the matrix, formed and aggregated in the solar accretion disk 4.5 billion years ago. Okay. And so here you have an artist's view of a disk, and here you have a real disk which has been imaged in the star forming region rho of. And what people believe too is that after chondrites, some chondrites are large enough to be hot enough and to melt, okay? And when you have a large body which melts, you have segregation between the metal, which will go into the core, and the silicates will remain outside. This is what happened for the Earth, for example, where all the iron has been sequestered into the core. So this is also what happened, with asteroids when they are large enough. And there are quite a few chondrite groups, but basically there are two main important ones. Ordinary chondrites, okay, which make up 80% of the meteorites falls. So they seem to be the most abundant of the meteorites. And ordinary chondrites are divided into three subtypes, H, L, and LL. And you have another group of carbonaceous chondrites, which are carbonaceous chondrites. They represent only a few percent of the falls, okay? So they don't seem to be as representative as the ordinary chondrites are, at least representative of the population which is falling now on Earth, because we know there is a bias in the way meteorites are delivered onto Earth. But carbonaceous chondrites are very important because they're very rich in organic matter, and for many other reasons, many people believe they are very primitive meteorites. They bring us the best record of the physical conditions in the disk. And so carbonaceous chondrites are divided into a few subgroups. And I'm going to mention a little bit the CI chondrites, which are very chemically, and the CV chondrites, which are very abundant, which contain many of these calcium aluminum rich inclusions. So this is a typical chondrite. It's called Renazzo. It's a Cr2 chondrite. And this is a chemical map, which was obtained with a scanning electron microscope at the Naturelle Muséum in London by Anton Kirsley. And the color coding is the following. Aluminium is white, magnesium is green, silicon is blue, calcium is yellow, and iron is red. So basically you have the map of the inside of a meteorite. Okay? And what you see is what we saw before, that the most abundant component of the meteorites are chondrules, which are like here. They are blue or green dominated, depending on the relative amount of magnesium and silicon they contain. Some chondrules, like this one, have an iron rim. That's typical of chondrules in some meteorites. Another important component are CAIs. And you can see here, at a glance, that CAIs in this kind of rock are very rare. You have only one here and another one here. Okay, so only two when you have maybe 100 chondrules. And the matrix, so the cement, which is purple and which is just bringing everything together. So, giving you a bit more details about what CIs and chondrules are made of. So this is a typical CI from Léoville. You can see scale bar, 600 micrometers. So it was cut in two here. So it was a relatively big object, a few millimeters in size. Okay. And it's made of high temperature minerals which are rich in calcium and aluminum, and which are believed to be refractory, meaning to have formed at very high temperature, between 515 and 2000 K. And these minerals are like called melillite, spinel, and andesite. And importantly, these sea ice have been dated using the lead-lead technique. I will talk about that later on. And it appeared that they formed 4.567 billion years ago. And they are so far, we will come back to that later, the oldest solids which have been dated. Okay? So they seem to be very important in that they formed very early and at very high temperature. And more than that, it was calculated in the early 70s by Larry Grossman that the mineralogy of CI is compatible with the mineralogy which you get from a gas of solar composition which cools. Okay, so you start with a gas of solar composition, the disk, and as it cools, you start to condense minerals, and the condensation sequence you calculate using thermodynamics. This is what Larry Grossman did. Is compatible, roughly, but quite good argument, with the observed mineralogy of sea ice. So this is this kind of diagram where you start with a gas of solar composition, and you cool it, and you start to condense the minerals. And so here you have a zoom of this region, and you can see that the first minerals you condense are calcium, aluminum-rich minerals such as corundum, ebonite, galenite, which is a form of melillite, the mineral which was very abundant in the sea I showed you before, spinel, which was present also there. Okay, and so not only was it calculated in the 1970s, but recently it was observed in the lab by Topani and collaborators. So they created a gas of roughly solar composition, which is not that easy, and they condensed it, and they observed the condensation products with a transmission electron microscope. And so these are the images with the diffraction patterns of the different minerals they could observe, and they could also roughly obtain the calculated condensation sequence. So CIs, at least some of them, condense from a gas of solar composition. It's compatible with their very old age. And you can also obtain some other constraints looking at the silicon and magnesium isotopic composition. So this is what Ed Young's lab did. And here you have a diagram where they try to constrain the time and the pressure at which the CI they studied was melted. Okay? And so basically this bound corresponds to the different possibilities. Okay? So either you have, they were melted at very high pressures for a very short amount of time, either they were heated at very low pressures for a longer amount of time. Still very short because this would correspond to 10 days. And physically, this situation will correspond to very few shock waves in the solar nebula. Okay, I will come back to this shock wave later on. And this would correspond to multiple solar flares in the accretion disk. Okay. So this is one example of how experimentally, so this is a result, this curve is a result of very challenging measurements of the isotopic composition of CIs. And so this is typically what people in cosmochemistry try to do to constrain the physical chemistry in the disk when CIs form. Now a little bit on chondrules. Chondrules are very important because they are very abundant. Okay, and so chondrules are made of these magnesium, iron, silicon-rich minerals, of which you might have heard: olivine, pyroxene. Okay, so that's all these guys you see here. They are made also of metal, reduced metal. Okay, which in this picture is here. That's the white stuff. So this is a scanning electron microscope picture of a chondrule within a meteorite. Okay. And they're also made of interstitial glass. So between the different minerals, which you see here, you have glass, okay, which is like the ground mass of the chondrule. Here is a zoom where you can see the glass between the olivine and the pyroxene crystals. So there is a great diversity among chondrules. Chondrules basically were noticed in meteorites a long time ago, at the very beginning of the 19th century, just at the time when people really finally understood that meteorites were coming from space. And it was actually a French immigrant in England who first described a chondrule in a meteorite. And though they've been known for so long and so many have been observed, we still don't really agree on how they form. And you have periodically new models for chondrule formation. And so these are 4 typical examples of chondrule types. So this is the most common type of chondrule called porphyritic chondrule. It's like an aggregate packing of all these olivine and pyroxene crystals. This is a barred olivine chondrule characterized by this bar of olivines. This is a radial pyroxene chondrule, and this is a compound chondrule. So this is, I think, a beautiful picture which was taken by Harold Connolly. And these are 2 chondrules which stick together. And the very existence and the relative abundance of these objects help modelers to constrain the conditions in which chondrule form.
Excuse me.
Yeah.
When there are compound chondrules, are they always the compounds of 2 of the same type?
That's a good question. I don't think so, no. I don't think so. It can happen that you have different types. But I don't know the exact numbers, but this is by far the most abundant type of chondrules. Barred olivine chondrules, such as here, are relatively rare. We tend to show them quite often because they're beautiful. So one way to understand chondrule formation is also to do experiments. So this is what people like Roger Ewins do. So they try in the lab to reproduce the texture of chondrule. So on the left, you have a real chondrule, which we saw before, which might be a few hundred micron across. And here are experiments. So you take what you think is the best chondrule analog you can make, and you melt it at different temperatures during different times and at different cooling rates, and you try to reproduce the texture of the chondrules. Okay, so this is inherited from experimental petrography, which is very much which is an important field in terrestrial geology. And from that experiments, you can constrain the conditions at which chondrules form. So it seems that chondrules were flash heated, meaning that they were brought to very high temperature in a very short amount of time. High temperature means maybe 1,500 K to 2,000 K, and this peak temperature was attained for minutes to hours. Okay, and they cooled relatively quickly at between 10 to 100 Kelvin per hour for porphyritic chondrules. It seems that chondrules like barred olivine chondrules cooled quicker. Okay. It seems also that many chondrules suffered repeated heating events. Okay, so that they were heated not only once but several times. Okay, that you make the chondrule by heating it, and then there is another heating event, and then another heating event, and they happen several times for each chondrule. And also, the formation of compound chondrules is an important constraint, as I said, to understand how they form.
Excuse me, Matthieu.
Yes?
So what are the evidence for repeated heating events?
The evidence, I think it's like the chemistry of the olivines and the pyroxene, the zoning or the absence of zoning, the C, the chemical composition.
But how can you expect to have multiple events that are exactly in the right temperature range, that you just, if you heat it a bit too much, you evaporate the whole thing. If you heat it not much enough, you don't get anything. So how? I mean, that sounds like a very big coincidence. In a way.
Very good question. I think that's what modelers try to do, to try to find a mechanism to make chondrules which is generic enough and can happen during maybe 2 to 3 million years. Okay. One constraint also is that chondrule formation maybe lasted for a few million years, if we believe the ages which are measured. We will see later on that there might be problems with these ages. But you know, many people believe that the chondrule formation could happen during 1, 2, 3 million years. And so you have to have an energy source which lasts that long, and as you mentioned, which always give you this range of temperature. So it's not easy. I think we can discuss. Some people here, like Jeff, have worked a lot on that, so after we can have a discussion about that. He knows a lot more than me how to solve these problems. So basically, just as a sketch, the chondrule formation sequence is that you have a precursor dust ball, which might be fluffy, which might have preserved some interstellar dust with it, and you have this kind of high energy event, whose origin is still debated, that goes through the chondrule, that goes through many of the precursors to create molten droplets, and then it cools, and to create a chondrule, which we now study. Okay, and as you said, it's puzzling, and this is important because we saw in the chondrites that chondrules represent maybe half of the mass of a chondrite, probably more. So if you believe that most asteroids in the asteroid belt are chondrites, which seems to be the case, okay, so it means that it was a very important, very widespread event that you need to identify. So probably at the moment, the most popular model for chondrule formation is a shockwave model, where you have a shockwave which goes through the disk and which very quickly, due to its shock nature, hits the chondrule to roughly the temperature which have been deduced from petrographical experiments, and which cool quickly after the shockwave has passed. Okay, so in that, so many people have worked on that, and so included Fred Schisler, and in this case, the shock speed in this peculiar model was roughly 8 kilometers per second. Okay. So this model is very efficient at reproducing the peak temperature and the cooling rates of chondrules, which are two important constraints, as well as the relative abundance of compound chondrules. Okay. Now the source of the shock wave is another question. You know, how can you have shock waves which last for a few million years in the disk? Okay, so several things have been proposed, like gravitational instabilities or Bow-shock planetesimals and things like that. But as you mentioned, it means that in a way you always need to have a shock wave of the same velocity to make the same kind of chondrules over a few million years. So one thing which is very important too, that there is a very large diversity between the different chondrites groups. Okay, so people talk about chondrites such, chondrites this, chondrites that, but if you look at carbonaceous chondrites and ordinary chondrites, you have relatively different rocks with different properties. Okay, and what distinguishes the different types of chondrites is the abundance and the size of chondrules and CIs, but CIs are less abundant, but also their bulk chemistry, you know, their oxygen isotopic composition, or their mineralogy. So here you have two examples. You have an ordinary chondrite, and you have very large chondrules, no CIs, and here you have a carbonaceous chondrite with smaller chondrules, okay, and with maybe a few percent of CIs. And this rock is very rich in carbon, and this rock is very poor in carbon. So this and that record different conditions in the protoplanetary disk. So this is also something that should never be forgotten. And coming back to the size of chondrules, so this can be an important constraint for astrophysicists. So this is the size of chondrules in x-axis. So phi is just a log of the diameter of the chondrules in millimeter. I don't know why that's. These guys have been using this unit for 20 years, and that's what they do. And this is just a standard deviation. So, but basically what you see is that you have CM chondrites with very small chondrules, typically 100 microns, and then you have CV chondrites with larger chondrules, maybe 700 microns, and you have LL, H, which are two subclasses of ordinary chondrites, which have larger chondrules. Okay. So the large chondrules are here, and the small chondrules are here. So what it means as, and it's really well sorted within one chondrite group. Okay. So it means that if you look at a CV, like a huge majority of the chondrules have, roughly 700 micrometer size. Okay. So it seems that there was some size sorting mechanism which operated.
The largest size there is a tenth of a millimeter?
Is what? Is 1 millimeter
The size
roughly.
for the LL is a tenth of a millimeter or a millimeter?
No, the largest size here is roughly 1 millimeter. So one way to interpret that you have all this, that each chondrite group has its own properties, is just to say that you have heliocentric zoning in the disk, okay? With ordinary chondrites coming from S asteroids, which are here, and Carbon-H chondrites, which come from C asteroids, P asteroids, and D asteroids, okay? Now, before I continue, beware of the biases, okay? Cosmochemists are always very assertive when they talk about the properties of the rocks, especially when they have spent 1 year in one chondrule and the second year in the second chondrule. After a while, they get a little bit, don't touch my chondrules. But they're always, the guy who works on ordinary chondrites, one chondrule, is like that. He tends to forget that what he describes is just one thing. And there are many biases, okay, in meteorite studies. One very important biases, everyone knows about it, but we always forget to mention it, is that most studies on CIs are made on CV3 CIs. Why? Because they're very big. I showed you at the beginning, they're maybe a few millimeters across, okay, so they're very easy to extract from the rock, and you have many of them. So it's not that people are lazy, but it's easier to study in detail a fragment of a rock which is a few millimeters across than a very little piece which is a tenth of a millimeter across. Okay, so most studies are biased towards CV3 CIs, and these are two CIs from other chondrites groups. So here you cannot see very well the scale bar, but it's 2 microns. So it's a very small object, maybe 10 micron across. And this one is 200 micron across, and they're very different from the CIs you find in CV3 chondrites. Okay, so there is a big bias. And again, CV chondrites, there are only a small fragments, a very small proportion of the chondrites, right? So there is no reason to take them as representative. When we talk about ages, I'm going to talk about ages in a minute. CIs from other groups are not dated with the lead system. We always talk about this age of the solar system being the age of these CIs, but it's only one type of CIs which have been dated. And don't forget that ordinary chondrites, which represent 80% of the meteorite swarm, they do not contain any CIs almost. Maybe you find one when you studied maybe 10 square centimeters of the rock. Okay. So there are biases. Another important property of chondrites, which you've heard probably, that they have the same chemical composition of the sun. So this is true of CI chondrites. So this is orgueil. This is the CI chondrites of which we have the largest mass, more than 10 kilograms. And if you plot the composition of this chondrite versus that of the sun, of the solar photosphere, it does agree over 900 of magnitude. Okay. Except for a few elements, and this is very well understood why there is some disagreement. Okay, so usually most modelists take CI chondrites as a disk starting composition because there is this agreement between the composition of this class of chondrites and that of the Sun. If you look at the chemistry of other chondrite types, you see some differences. So here, this is a plot of the chemical abundances of different types of chondrites normalized to CI chondrites. Okay, so if it was exactly the same, you would have one here. And you can see, for example, if you look at CM chondrites, that they are very enriched relative to CI and the Sun on refractory elements, aluminium, scandium, calcium, and they are depleted, again, relative to the CI composition in more volatile elements. Here, the elements are arranged in order of volatility. Okay? So maybe the disk almost never had a CI composition. It's not because the Sun, has a CI composition that the disk had one. Okay? Maybe it had one for a very transient moment. I think we should try, and you know that a lot better than me, try to see the disk as something very dynamic and not as a nebula, which is something very static and doesn't move with time. I think I'm gonna skip that. Maybe we'll come back later. Another constraint brought on from meteorites too is that in some carbonaceous chondrites, you have a lot of insoluble organic matter, which has been studied in detail and which has large isotopic anomalies. So here is a plot which shows the different enrichments in delta 15 of your samples relative to Earth. Okay, so any sample from Earth would be around 0. So you can see that you have huge enrichments. And in this case, which is an inclusion from Isheyevo, which we studied, the 15 nitrogen to 14 nitrogen ratio is like 5 times higher than what you find on Earth. Okay, so it's a huge isotopic anomaly. And no one really understands how it was formed. So maybe it was due to UV photochemistry in the ISM or in the disk, but really at the moment, no one really knows. But this is probably a very important constraint on the disk evolution. I've not talked about matrix. Why have I not? Why? Because in most chondrites, the matrix has been transformed by geological processes. What does it mean? It means that a chondrite, comes from an asteroid, which is a small planetary body, and in which you have geological processes such as metamorphism or hydrothermal alteration. And since matrix is so small, it is more easily altered, transformed by these geological processes and chondrules and or CIs. It's just a matter of surface to volume ratio, right? For example, if you have a fluid interacting with the rock, the matrix, which is very small, has more surface area and will interact more with the fluid than the chondrules. Okay, so the matrix in most occurrences is totally blurred, has been totally transformed by geological processes. So in some primitive meteorites, you still have pristine matrix, and which seems to be made of olivine, pyroxene, a lot of amorphous material. And this is in the matrix too that people have found something which is very important, which are called presolar grains. So presolar grains are very tiny solids, maybe 1 micron in size or below, and which have an isotopic composition totally different from that of the solar system. And this is interpreted as a sign that these presolar grains were formed around other stars which predated the formation of our solar system. And for some reason, mostly because they are very refractory and very hard minerals, they've not been destroyed by processing in the disk, nor by processing during the geological life of the chondrites. And just to confuse you a bit more, there is this recent work, which I really like. So I cannot show it in detail because it was just presented at a conference, but Ben Weiss from MIT showed that Allende, which is a chondrite, a CV3 chondrite, has a paleo field, okay, and the properties of this paleo field seem to be consistent for with IND coming from a differentiated parent body. So basically you have a chondrite, IND, which was sitting at the surface of a differentiated parent body, which created the dynamo. Okay, to create a dynamo, you need to have a core, so you need to be differentiated. So if you look at a chondrite, you would not expect, okay, to find any record of a dynamo, and this is what you found. So maybe it's even more complex than we think, with differentiated asteroids, which have a crust of primitive components.
Sorry?
Yeah.
Alain, is a find or a fall?
It's a fall. It's a fall. It fell in 1969 in Mexico. And this is one of the most studied rock because tons of it fell. So that's why people are very keen on studying IND. This I will skip. So now we're going to talk a little bit about chronology. So this is a French sculptor called César who did that in the 70s. And chronology relies on radioactive, and this is a bit like what chronology in meteorite looks like. just pick up your clock and that's and you will get something. Chronology relies on radioactive elements, and we usually use two types of radioactive elements: long-lived ones, which have a half-life of roughly 1 billion years, and short-lived radionuclides, which have a half-life below 100 million years. And to do chronology, you need to make a huge assumption, which is that the radioactive element you're using to build up a chronology was homogeneously distributed in the disk, okay, spatially, okay, at the beginning. So it means first that you have decided of a very clear beginning, which is a not that easy concept, you know. How do you define the beginning of the solar accretion disk when you know that during the first phases it is still embedded in the envelope and you have a lot of interstellar gas and solids coming through it, and so I never really understood why we should have a starting point. And so you need to assume that these elements were homogeneously distributed at the beginning to do chronology. So the long-lived radionuclides which are used are uranium-238 and uranium-235. They have respective half-life of 4.5 and 0.7 giga-year, and you can combine these two short-lived radionuclides, and the best labs in the world, which do an absolute incredible work, can have errors on the ages of 0.1 million years. Okay, and these are absolute ages, so you really date, you know, the age of your component. And short-lived radionuclides, the ones which are most used are aluminium-26 and hafnium-182, which have respective half-lives of 0.7 and 9 million years. And short-lived radionuclides, they give relative ages. Okay, so they've totally decayed. Okay, so you cannot go back in time. You just, if you have different amount of short-lived radionuclides in different samples, you can tell which form first and which form second and what is the time difference. But you need these absolute ages as an anchor if you want to do the full chronology.
Matthieu, sorry. I understand how the relative ages obviously require this assumption of homogeneity that you mentioned.
Yeah.
So comparing two different things. Do the absolute ages also rely?
Yeah, they also rely, I will talk about that in a minute. They also rely on the fact that the ratio of uranium-238 to uranium-235 is constant in everywhere. Okay, which is now a question. Okay, so short-lived radionuclides, they are totally extinct now because their half-life is shorter than the age of the solar system. Okay, and since they are extinct, how does it work? So it's relatively easy to understand. You take a rock, you separate several minerals, and for example here for aluminium-26, which decays to magnesium-26, you plot the magnesium isotopic composition in different minerals versus the aluminium to magnesium ratio. Okay? And what you see is that the minerals which are enriched in aluminium, okay, which are aluminium rich, have very anormal isotopic composition. They are very enriched in magnesium-26. Every terrestrial sample in this plot will plot here, okay? Any sample from the Earth will plot here. So this is a large excess. This was measured in the 1977. This is a very classical, important paper. And so what you can see that the richer in aluminum you are, the more excess of magnesium-26 you have. And this correlation between the isotopic excess and aluminum-27 demonstrate that there was some aluminum-26. And from the slope in this diagram, which is called the isochron diagram, you can deduce the aluminum-26 to the aluminum-27 ratio. So this is the first CI which was ever measured. This is the first sample in which an excess of magnesium-26 was ever discovered. And they showed that the aluminum-26 to 27 ratio was 5, 10 to the minus 5 when the CI is studied form. Okay, we'll see that. So again, when you want to do relative chronology, you want to have a time 0. And what people usually take are CIs because they have this very old lead age. Okay, so you will do chronology always relative to CIs. So again, many people have measured aluminum-26 in CI. So this is some work we did with Edion a few years ago, and we found exactly the same thing as Lee and Papanastasiou and Wasserberg found 30 years back. That when this CI from Léoville formed, it formed with roughly 5, 10 to the minus 5, aluminum-26 to minus 27. So now let's look at controls. So this is a recent work by Villeneuve et al. And they look again at the magnesium-26 excess. So this is a strange unit. So this is just the excess of magnesium-26 versus the aluminum to magnesium ratio. You can see that there is this correlation. And they deduce from that correlation that this control formed with aluminum-26 to aluminum-27 of roughly 1, 10 to the minus 5. Okay, 8, 10 to the minus 6. So if you use a very simple equation, basically there is a factor of 5 difference in the initial content. Okay, so 5 is roughly 2 square. Okay, so it's roughly 2 half-life, basically. So 2 half-life of aluminum-26 is 1.5 million years. So controls from 1.5 million years after CIs. Okay. And this is also what has been measured recently by lead ages. So I will not describe you these diagrams, which are a bit more complicated, and I have no time. So IND-CIs measured with the lead technique, they are 4,567.7 million years old, and IND controls measured with the same technique are roughly 1.6 million years old. So it seems that the lead technique does confirm this age difference seen with aluminum-26. Now you have eucrites, which come from the differentiated asteroid Vesta, and these eucrites, it seems they form with aluminum-26 to aluminum-27 of roughly 7.5, 10 to the minus 7. And so these eucrites form 4.4 million years after CIs. So a very simple model to understand. CIs form first. You wait 1.6 million years. You form chondrules. When chondrules are formed, you form chondritic parent bodies. If these chondritic parent bodies are large enough, they differentiate. Okay. And the crust of this differentiated asteroid is a eucrite, which formed 4.4 million years after CIs. So this was a view a few years ago. So this view had also some problems. One problem was pointed out many years ago by Stu Weidenschilling. It's like the storage time. How do you store CIs in the disk for 2 million years? Because you would expect them to drift in the nebula. And Jeff Cousy probably will talk about it more, but proposed that diffusion of solids in turbulent disk can help to solve that problem. Though I think it's a bit difficult because you still need to be group specific. Now this nice chronology, which I mentioned before, seems to be in trouble. So using the 182 hafnium radionuclide, people have dated iron meteorites. So this is a picture of an iron meteorite. Iron meteorites are supposed to come from the core of a large asteroid. Okay, so very evolved samples. So you would expect them to form late, right? And what they found using this technique is that the age of iron meteorites relative to sea ice is the same. Okay, there is even that sample which is slightly younger than sea ice, older than sea ice. Sorry. Okay, so it seems that iron meteorites are formed contemporaneously with sea ice. So this was a big surprise. I'm going to skip that. And this surprise is also, in a way, confirmed or supported by lead-lead measurement of this rock. So this is not a eucrite. It looks like a eucrite. It comes from the crust of a large asteroid, but probably not from Vesta, because it has a different oxygen isotopic composition from eucrites. And it's been dated by the lead-lead technique, and Hamlin, which is one of the lead-lead experts in the world, got this age of 4,566 million years. Okay, so it's older than chondrules. So it seems that you have at least two suites of samples which are evolved, which are differentiated, which are as old as sea ice. Okay. Now, just a word of caution. It's not easy to measure lead ages. It's extremely difficult. Okay. And Yuri Hamlin himself mentioned recently that there might be, some biases due to the analytical technique. And also, very recently, it was suggested, so this is a basic equation, the fundamental equation of lead-lead dating, okay? So basically, you deduce the age, which is here, from these measured quantities, and this is a ratio 238 to 235, which is always assumed to be constant and have this value throughout the disk. Okay, so people assume it is the same in the CI forming region, in chondrule forming region, everywhere. Now, recently, this group from Arizona, Breneka, Vadva, and collaborators, have measured the uranium isotopic composition of different chondrite groups and some CIs. And they found big differences. And for CIs, they find differences that large that they say that this difference of up to minus 3.5 per mil implies that a correction of up to minus 5 million years would be required. So maybe one of the fundamental assumptions of lead-lead dating, which was this homogeneity of the uranium isotopic ratio, is questioned. Okay, so we have very accurate age, okay, measured by very skillful people, but maybe there was one assumption that everyone made because you have no other choice so far, which is wrong. So take the ages with precaution. This would
May I
be.
ask a question here?
Yes, sure.
But if that is like 5 million years of uncertainty, you would then also find a couple of measurements that would be clearly out of bounds, because you would then expect to have some rocks that are older than the solar system, basically, than everything that has been measured so far.
Yeah.
But I've never heard of that. So
There is some spread in the lead ages of CIs. Okay, so some people find 4, 5, 6, 8, some 4, 5, 6, 6. Okay, so there is spread maybe of 2 million years.
but that's 5 million.
But that's 5 million years. But that's not exactly the same CIs they look at, right? So this could be explained why. But that's a good, that's a very good point. And also remember, once again, that this assumption of homogeneity of aluminum-26 and other short lava nuclides has never been demonstrated. Okay, so for example, this is a plot, an old plot of the distribution of aluminum-26 in CAIs, and you can see that there is a large peak at 5 × 10⁻⁵, which is taken as time 0, but you have also many CAIs which form with no aluminum-26 and some with intermediary values. So this assumption of homogeneity is still to be demonstrated. So keeping that difficulties in mind, this would be the present chronology, with first the formation of unknown chondrite groups. We don't know them, we have no samples. They have differentiated to make large asteroids, and this is an iron meteorite, which is very old. and which has the same age of the sea ice we know now. And then after 1.6 million years, you have chondrules, which we know now which form. And once these chondrules have formed, have agglomerated together with sea ice, they can make large bodies which differentiate, and they can make samples like eukaryotes, which come from Vesta. So it's a more complicated chronology, especially since we have no clue what these guys are. And I find it very interesting, and this is something that could be discussed here, is that this seems to imply that accretion was very fast, okay? Because it's doubtful we go back maybe million years before, right? And this seems to imply that accretion was very slow, because you had to wait like 1.6 million years between the time you make these guys and the time you make these ones. This very quickly. So there is a recent proposition about chondrules which tend to support this new chronological view. This is Libourel and Crott, dates back in 2007. So they looked at chondrules in detail. These guys are very good petrographs, so they know what rocks mean when they look at the texture of the rock. And what they showed is that in chondrules you have a lot of this triple junction, okay, which like you have 120 degrees angle between each olivine crystals. And this is typical of planetary mantles. So what these guys claim is that chondrules formed from debris of previous generation of planetesimals. Okay, so exactly what is consistent with this view, where you have a first generation of chondrules, where you have a first generation of differentiated planetesimals which have a mantle, okay, before the formation of these chondrules. There is one, so as you noticed, I did not enter too much into models because there are so many modelers here that I did not want to say too many wrong things, but there is one model which might explain also why some objects accreted very fast and some other accreted more slowly. So this is a simulation done by Bill Bottke and others when they look at the orbital evolutions of asteroids. This is the blue, the red, and the yellow dots formed in the very inner solar system, and the embryos are the gray dots. And what they show is that after 10 million years of dynamical evolution, all these guys, which started here, okay, a significant portion of them end in the asteroid belt. So it could be that some of the guys that differentiated very quickly were just formed closer to the sun than the asteroids which formed in the asteroid belt. And this is understandable because the closer to the sun you are, the faster the accretion is. Okay, so this model, in a way, explains this data. And very recently, there is this beautiful work by Bland and collaborators from Imperial College. So they have devised this camera network in Australia to try to catch meteorites falling on the ground and to determine their orbit. And so they did, and this is a first meteorite. And so this is a fireball, okay? This is a meteorite on the ground, we just studied, and it seems to be a very weird rock, so it's extremely interesting that the first meteorite they got is different from any other meteorite we knew before. It's like a eukaryote, but not exactly. And the orbit of this meteorite is internal, it is an Athens-like orbit, it's internal to the Earth. Okay. And the properties, this is a differentiated meteorite. So this could be one of these samples, also one sample of something which formed very close to the sun very early. It's not been dated yet, but I'm sure they're going to do it soon. I'm almost out of time, so very quickly, transport and mixing. So a very important feature of the solar accretion disk is that there was a lot of transport and mixing between the inner zones and the outer zones. So in sea ice, there was one short-lived nuclide which was discovered a few years ago, beryllium-10. And this guy was probably made by irradiation very close to the sun, okay, by cosmic ray irradiation. And this cosmic ray irradiation occurs close to the sun, where the cosmic rays are not stopped by the column density of the disk, okay. So basically, you have CAIs have been very close to the sun, okay, maybe 0.6 AU from the sun. And now they are within asteroids, which you find some AUs from the sun. Okay, so it seemed that there was some big transport from the very inner solar system to the asteroid belt. And more spectacularly, you've heard about the Stardust mission, which brought back maybe 1,000 grains of cometary dust recently. And in the Stardust sample, people very unexpectedly found one CI, maybe a few, and some chondrules. Okay? And so not only they found CIs and chondrules, which was totally unexpected, but these CIs and chondrules have the same properties from the, for example, as far as the oxygen isotopic composition is concerned, as CIs and chondrules in carbonaceous chondrites. So VIL2 dust analysis tell us that cometary dust looks very much like carbonaceous chondrites dust. That there is also a continuum between asteroids and comets, okay? Because people were expecting the cometary dust to be very different from the asteroidal dust. It's not the same. It's not the case. It looks very similar. There is really a continuum between these two types of objects. And CIs in the comet-forming regions mean that there is a large-scale transport. So these transport mechanisms will be probably discussed a lot later on. And there are mainly two possibilities which have been recently discussed. Either outward diffusion in a viscous disk. There was a recent very nice paper by Chisla in 2007. And wind transport, X-wind transport, from the inner part of the disk to the asteroidal distances. I must say that, as some people know, I have some proximity to this model. But I must say there is something which really strikes me, which is that Frank Shu in 1996 wrote that you should expect to have CIs in comets. And it was a prediction, in a way, of his model. And at the time, no one believed it. And you know, some 20 years later, the CIs were found in the comet. So though both explanations might be true, they are totally compatible one with the other, they're not exclusive. I think it's very nice to be able to make a bold prediction and to have it realized. So very quickly to conclude, we have a very great diversity of extremely complex rocks. Many of the processes we try to understand are blurred by geological processes, so it makes our life difficult. The different groups of chondrites do not record the solar nebula as a static thing, you know, that would have existed for a million years. But it records a spatial and temporal variation, and it's very difficult to disentangle what is due to spatial evolution, to spatial heterogeneity, or to temporal evolutions. And chronology is very difficult because of the measurements and because whatever people say, they always make assumptions. And just to be a bit more positive, so primitivity is questioned. Okay, that's something which I think is important. We could think about why accretion sometimes is fast and sometimes is slow, if the ages are correct. But as I said, we should keep in mind that there might be some problems. And I think there are many, many data on meteorites, many of them. And what we lack are not data, but what we like is bright people to think about it. So it would be great if more astrophysicists and theoreticians come and help us to think about this data. Thank you.
That was great, thank you. So we already had many questions during the talk. Do we have a few more before we break? Yeah, Sebastian?
In the different scenarios that you described based on the chronology, how many parent bodies do we actually are we actually probing? Is it just an handful? on them, or is it?
Yeah, it's only a handful. It's more than what I talked about, right? Because there are many more data than the ones I showed. Like there are another important group of differentiated meteorite, which is called angrite, which is quite well dated, and is different from Vesta. And you have mesosiderite. You have a handful of them, yes. A bit more than what I showed, but not that many.
No?
Just because you find a meteorite coming in on an orbit from an auton doesn't mean it formed in an auton's orbit by a long shot.
Right.
So,
Oh, yeah.
you know,
Okay.
everybody is moving around, and you know, it's great to feel loved.
Yeah.
I've never seen a slide like that that asks
Yeah. Yeah.
for
no,
more
you're right.
theoreticians.
I was a bit too over enthusiastic about this paper, but yeah, you're right.
You said that big bodies grow out of chondrules most probably, and so this means that when you pass the millimeter size, the density increases a lot. You come from aggregates of dust to a kind of rock. And I'm wondering if this should not be taken into account in all the models of accreting dust, and maybe it would help to pass the meter size barrier, because obviously an aggregate of chondrules would not behave like an aggregate of dust, I think. Does it make sense to assume that everything that is more larger than a millimeter should be more dense than just dust?
I guess so. It's a good point. I mean, it seems that there are known of very few chondrules which are larger than a few millimeters. So it seems that there is or CIs. It seems that there is this barrier between 1 millimeter and 1 centimeter, where it does not grow anymore as an individual chondrule or CI, but as an aggregate. It's a good point.
A question myself. You mentioned this result by Villeneuve et al. On the time delay of chondrules, but if I remember well, what they find in addition is that there is a big spread of chondrule times inside the same chondrite, which is surprising because, as you said, there is a very good size sorting and chemical sorting inside these meteorites. And there is no time sort.
Yeah.
You can get chondrules from it, ages ranging over 1 million years.
Yeah, I do agree. That's something I should have talked a bit more about. We discussed it a little bit. There was one question. Yeah, there was this time span. People observe this time span for forming chondrule. It's quite unlikely, as Alessandro says. Maybe it's due to some age resetting too. You know, some objects appear younger than what they are because of these geological processes on the parent body. And this is especially true for chondrules, because when you want to date a chondrule, you want to have aluminium-rich phases, okay? And what are to have this isochrone, right? To have the lever. But what is the aluminium-rich phases in chondrules? This is glass, okay? And glass is a lot more susceptible to reset than any other mineral, right? Because you heat it a little bit and all the elements start to move around. So it could be that some or many or all of the chondrule ages are biased as far as aluminum-26 system is concerned by these measurements in glass. So keep that in mind too.
Okay, I think we should stop here to have some time for the break. I remind you the coffee break, tea break in the afternoon is also the poster session, so I would encourage you to grab a cup and move to see the posters, and in particular the poster presenters to be there by their poster. So we reconvene at 3:30.